So anyways, 9.1 and 9.2. Are about systems of linear equations. Systems of linear equations. Now, a system of linear equations, it's just multiple linear equations as a set, right? So a system of linear equations is just a set or a group of linear equations. I want to use the word set there. No, that's going to make it different, but to be a little bit more mathematically accurate. So for instance, if we have x plus 3y equals 17 and 4x minus 2y equals 11, that is a system of linear equations. Okay. Now, we're going to be looking for a solution to the system, right? And a solution to the system is a point or an ordered pair. Which makes all of the equations true. So it's a single point that makes all the equations true. All right. Most systems are going to have one point that works. Right? Most systems. And we're going to think about having two variables and two equations. So think about having two variables and two equations. If I have two variables and two equations, that means I have two lines and I have two dimensions. So I have two lines in the Cartesian coordinate plane. And if you think about the types of solutions that picture can produce, if I have two lines in the Cartesian coordinate plane, let me draw this a little bit different. It looks like it's perpendicular. It doesn't have to be perpendicular. There. The point that they cross is going to be a solution because it's going to make both equations true, right? So most of the time, we're going to be in the one solution case where the two lines cross at a single point. Another case, though, is where I have two lines that are parallel. Well, parallel lines never cross. So if lines are parallel, we have no solution. And lastly, if the lines are actually the same line, we have infinitely many solutions, infinitely many points that satisfy both equations. All right. As far as let me rephrase this. So this is the two equations and two variables case, all right? But the same is going to be true for any number of equations and any number of variables. We're either going to have one solution, no solutions, or infinitely many solutions. The two variables, two equations case is nice because you can draw pictures in the Cartesian coordinate planes. It's much harder to do that if you got three equations and three variables, or if you have three equations and two variables. You still end up with the one solution, no solutions, or infinitely many. So no matter how many equations and variables, these are the three different types of solutions. And again, the pictures hold true for the two equations, two variables case. That's the one that we're going to use most often. But it would also hold true for any number of variables, any number of equations. All right. Now, as far as the terminology goes that you may see the word consistent. System of linear equations is consistent. That's another way of saying just it has a solution. And by a solution, we mean either it has one solution or it has infinitely many. Okay, consistent means it has at least one solution. Inconsistent means the system has no solution. This is not terminology that I'm gonna like quiz you on or anything like that. But if you're reading along in the book and you see these words, I want you to at least have seen them before, kind of know what they mean, or at least be able to look them up. Then we have the solution is independent. Shoot. And dependent. Independent means essentially we have one solution. A dependent system means we have more than one solution. And in this case, that only leads us to the infinitely many solutions, right? So if you're reading along the book and they say, oh, this is a system which is consistent and independent, that just means it has one solution. Okay. Now, what we're going to want to do in chapter 9 is solve systems of linear equations. Okay. So we're going to be solving systems of linear equations. And we're going to use one of a couple of methods in this section. And then we'll see a few methods using matrices in 9, 5, and beyond. All right. So in this section, we use either one, substitution, or two, the addition, or sometimes people call this the elimination method. Right? So we'll look at a couple of those. All right. So let's start with substitution. We're going to use substitution to solve the following system. Y equals 2x minus 4 and 4x minus, oops, said 4x or y, 4x minus y is equal to 38. And I'll kind of write down what I'm doing as we go through. So substitution is really nice when one of our equations already has y equals or x equals in it, right? In this case, my first equation already has a y equals. So I'm going to replace the y in the other equation with the 2x minus 4. So I take 4x minus y equals 38. And I replace or substitute the 2x minus 4 in for y. That makes sense? Once I do that, then I can solve and get a value for x. There's no y's in here. So now I can solve and get a value for x. Make sure when you do substitute, you put whatever the expression is inside of parentheses, because this minus out front is going to have to distribute. So we're getting 4x minus 2x plus 4 is equal to 38. I'm going to do a couple of things at the same time. I'm going to subtract 4 from both sides. And then combine like terms on the left. So I get 2x is equal to 34. And if I divide both sides by 2, I get x equals 17. Oh, shoot. Now that I have x equals 17, I do another substitution. I just substitute in that 17, or I plug in the 17 in for x. And I'll do that in my first equation because that one's already solved for y. So I take my first equation, and I believe I get 30. I'm trying to do that in my head, but I believe I get 30 there. And so that's my solution. My solution is the point 17, 30. X is 17, y is 30. And it's an ordered pair because it had two variables. Right. So that's substitution. Substitution works really well when we have one equation which is already y equals something, or one equation which is x equals something. And the something would not involve y's, obviously, or x's. Like in this case, you don't want y equals 2y. That's, you don't want to substitute in y for another expression including y. But as long as y equals an expression in x, we can do that substitution process. It doesn't matter that in this case it was my first equation. It doesn't matter that it was y. Let's do one other. Let's say I have 5x minus 2y equals 18. And x equals, actually, no, let me do y equals again, sorry. Y equals 3x plus 9. Go ahead and try this on your own. More common to get y equals on these things. Although in question 4, there is an x equals. All right, so in this case, we have y equals an expression in the second equation. So we're going to replace the y in the first equation with that expression, specifically the 3x plus 9. If I do that, make sure you put the 3x plus 9 in parentheses because you're gonna have to distribute the -2. Into both terms, right? So be careful about that. Adding 18 to both sides gives you a 36. To get -1x is equal to 36, which means that x has to be -36, dividing both sides by -1. So I replace x with -36. And in this case, it's easier to put it into the second equation. So I'm gonna do that. Y equals 3 times -36 plus 9. 3 times -36 plus 9 is -99. So the solution is the point -36, comma, -99. So that's substitution. Substitution works best when I have x equals an expression in y, or y equals an expression in x, and then I can just replace that variable in my other equation. Any questions about substitution? What about that? Okay. All right, so let's start using the elimination or the addition method now. And this one's kind of an interesting method. So we're going to use the elimination or the addition method to solve. Let's say I have 4x plus 3y equals 8. And then 2x minus 5y equals what? I made these numbers up, so I might get some ugly decimals. That's all right. I get some ugly numerical values. I think you get fairly nice numbers on the homework problems. But okay, so the goal is to create opposite coefficients on either the x's or the y's. I think what I will do is I'll try to create opposite coefficients on the y's. Okay, So I will create opposite coefficients on the y's. Somebody else may create opposite coefficients on the x's. So here's how we do it. We look at the coefficients of the y's. And I write the -5 coefficient of the y in the second equation. I'm going to write that in front of the first equation. Okay. So we put coefficients of our y's in front of the other equation and change the signs on one of them. Change the sign on one of them. Let me explain what I mean here. I take 4x plus 3y equals 8. And 2x minus 5y equals 12. I'm going to put a -5 in front of the first equation because of that -5. I'm going to put a 3 in front of the other equation because of that 3. And then I need to change the sign on one of these. So I can either make this 3 a -3, or I can make this 5 a +5. And generally, I like to multiply by positives. So I'm going to change that -5 into a +5. Oh, maybe I didn't write this to begin with, but elimination, addition works best when I have things all lined up. I missed that part. I didn't say that part to the beginning. So I need things lined up for elimination to work in column. And then I do that. But all the ones that I give you and I say use elimination for this, they will already be lined up. Okay. So then I multiply through. I'm going to get 20x plus 15y is equal to 40 in the first equation. And I'm going to get 6x minus 15y equals 36 in the second equation. Now, this is why it's called elimination. Once I've done that, once I've created those opposite coefficients, I can add the two equations together vertically. And that adding the two equations together will eliminate my variable y. So I'm going to get 26 times x, the y's cancel out, is equal to 76. $76 divided by 26 is not a very nice number. It's 39/13 simplified. So divide both sides by 26 and we solve for x. Simplified, it's 38 over 13. Okay. And Moodle, you can round your answers to 2 decimal places. Now at this point, we have some options. If I want to plug in 38 over 13 in for an x and solve for y, I can do that. It's perfectly fine. That's what most times I do. Most times we have a nice number, so it's easier to plug in. Here it's kind of an ugly number, so it's a little bit harder to plug in, but you can do it anyways. And you can do it in either equation. I think I'll use the first equation. So that's 152 over 13 plus 3y equals 8. I'll subtract 152 over 13 and then divide by 3. I get 48 over negative 48 over 13 equals 3y. And then divide that by 3. I get negative 16 over 13. So my solution is ugly fractions, but that's okay, still a solution. X value is 38 over 13, Y value is negative 16 over 13. Again, in Moodle, it'll ask you to put your answer, round your decimal answers to a couple of decimal places. So this is what I usually do. I plug in the number. Some people get really, really good at elimination. So when they end up with an X like 38 over 13, instead of plugging it in and solving, they actually say, well, it's just as easy for me to go back. I eliminated the Y's. They go back and do it again with eliminating the X's. And so that's also a possibility. Let's do another elimination addition method. Let's take 2x minus 4y equals actually do 2. And then 3x minus 5y equals 5. Okay. And we'll use elimination or addition to solve it. Now again, if I want to use elimination and addition, I need to make sure that things are lined up vertically. My x's are in the same column, my y's are in the same column, my equal signs, and my constants are all in the same column. So make sure things are aligned vertically. Things are aligned vertically. So now I can use the elimination. I'm going to, well, which would you rather eliminate, the x or the y? The x variable or the y variable? Any preference? I don't have one.
X.
X, all right, so we'll eliminate x this time. So we're gonna eliminate x. So we're gonna write 3 in front of the first equation. And I'm gonna write 2 in front of the second equation. And I have to change one of the signs. So both of these were positive. Therefore, I need to change one into a negative. It doesn't matter which, so I'll just use -2. Right? Now I multiply through. 3 times 2x is 6x. 3 times -4y is -12y. 3 times 2 is 6. And then when I multiply it by a -2, I get -6x plus 10y equals -10. Add my equations together vertically. This is why they had to be aligned. And I end up with -2y is equal to -4. So if -2y is equal to -4, dividing both sides by 2, you get y is equal to 2. Excuse me, dividing both sides by -2, you get y is equal to 2. And then again, as always, you can either plug in the y into one of these equations and solve, or if you wanted to, you could actually go through and eliminate the x, or you've already eliminated the x, so you can eliminate the y by writing -5 in front of the first equation, -4 in front of the second equation, and then changing a sign. So if you wanted to do that, you could do that as well. I'll say this, in the one we did last time, I tend to do an elimination method. Sometimes that's quicker when you get really ugly fractions. But when you get nice numbers like whole numbers, 2, or integers, a lot of times it's easier to just plug in. So I'm gonna plug it in. I'm gonna plug in 2, 4, y, and it doesn't matter, first equation, I guess. So I take my first equation, and I plug in 2 for y. add 8 to both sides, divide by 2. And we find that our solution has an x value of 5. Y value. So y value is 2, x value is 5. By the way, make sure that if you eliminate the x first, or whether you eliminate the y first, whichever, whatever your solution is, make sure you put in x, comma, y, right? Don't accidentally put in 2, 5, because that would be backwards. Any questions about that? That technique, pretty straightforward. Just make sure everything's aligned, and then whatever the coefficients of x are, if you want to eliminate the x, you put those in front of the other equation, change the sign on one. And if you want to eliminate the y's, you put those in front of the coefficients of y's in front of the other equation, and then change the sign on one of them. That's always guaranteed to get you opposite coefficients on whichever variable we're trying to eliminate. So on all of these, on all 4 of these we've done, the solution has come back as a nice ordered pair. There are scenarios where we get those infinitely many solutions or no solutions, okay? And in that case, what's gonna happen is both variables are gonna drop out at the same time. And so in this step, when we do the elimination, not only does my x get canceled out, but also my y. And I get like 0 equals -4. And if I got 0 equals -4, that's a false statement, so that's a no solution case. Does that make sense? Let me do a real quick one. And I'll use the elimination, but this could happen in the substitution method as well. All right. So elimination, let's say we had x plus 2y equals 6, and 3x plus 6y equals 0. Let's say we want to, well, things are aligned vertically already, so we say probably elimination. And so let's eliminate the x. I'm going to put a 3 in front of my first equation. And I'm going to put, well, the coefficient in my first equation in front of the x is a 1. So I'm going to put a 1 in front of my second equation. And then I make one of those into a negative. I think I'll use -3. Because 1 times anything is itself, so you can kind of, when I multiply 3 by 1, that's a really easy multiplication. So -3 times x gives me -3x. -3 times 2y gives me -6y. -3 times 6 gives me a -18. Multiplying by 1 doesn't change any of the terms in the second equation. 1 times 3x is 3x. 1 times 6y is 6y. And 1 times 0 is 0. Now when I add these things up, both the x's and the y's are eliminated. So on the left-hand side of the equal sign, I get a 0. And on the right-hand side of the equal sign, I get a negative 18. Now, 0 equaling negative 18 is a false statement. 0 is not the same thing as negative 18. So that tells me the system has no solution. If we ended up with 0 equals 0, or 5 equals 5, or negative 32 is equal to negative 32, if we got a true statement, that would be the case where we get infinitely many solutions, right? So I'm going to write that a true statement would be that system has infinitely many solutions. So if we have a false statement, that means no solution. And a true statement means we have infinitely many solutions. At that stage, obviously. A lot of the problems in the book, civils are not in the book, in Moodle, will say use any method. So just use the one that makes most sense. If things are aligned, use the elimination method. If you have y equals something in one of the equations, substitution is probably easier. Okay. Now, another thing, and I'm just going to do one problem of this. Another scenario that we can come up with is, let's say we have 3 solutions and 3 variables. Not did I say 3 solutions? I'm sorry. 3 equations and 3 variables. So let's say we have x minus y plus z equals 0. And then we have 2x plus y plus 3z equaling 23. I'm trying to make it so that this will come out nicely. All right. And then we have x plus y minus 5z equals, excuse me, 2. Now, if we are going to do this problem, what we want to go with is we want to go from 3 equations, 3 variables, down to 2 equations, 2 variables. That's the goal. So the goal is to eliminate a variable and get 2 equations with 2 variables. All right. So what we do is we pick 2 pairs of equations and we eliminate the same variable in each pair. So let's pick a pair and let's go with equations 1 and equation 2. And we'll eliminate y in that. And then we'll do another pair. We'll do equation, well, it can't be 1 and 2 again, so you can pick either 3 and 1 or 3 and 2. Does that make sense? Yeah, preference 3 and 2.
Probably 3 and 1.
Yeah, let's do 3 and 1. That's good. Equation 3 and equation 1. And we'll also eliminate y. So we're kind of take equation 1 and equation 2 together. And we'll eliminate the y there. And then we'll take equation 1 and equation 3. And we'll eliminate the y there. Now, we made good picks. We were smart enough to look ahead a little bit and say, yeah, it's going to be fairly easy to eliminate the y's in this pair, equation 1, equation 2 pair, because we already start with opposite coefficients. In that case, multiplying is not going to really help me very much. And then equation 1 and equation 3 also had opposite coefficients. So that was really nice too. So basically, I don't need to do that trick where I multiply by the coefficients on the opposite equations and then change one sign. I can simply add the two equations up in both cases. I made this one fairly straightforward so that we could do that, okay? This one will give me 3x plus 4z equals 23. And this one will give me 2x minus 4z is equal to 2. And now I have two equations in two variables. So I create a system with two equations and two variables. And I'm going to solve this system. Well, once again, the nice thing about this one, and they usually don't always work out this way. I'm giving you sort of the nicest version of this, so we don't have to do a lot of work. But this one already has opposite coefficients on the z's. So if we eliminate the z's by adding the two equations together, we end up with 5x is equal to 25, which means x has to be 5. Once I know that x has to be 5, I can plug that into one of these equations and find my z. So I'm plugging that in. X equals 5 into this one. You could also plug it into this one, doesn't matter. Subtract 15 from both sides. We get 4z is equal to 8. So z is 2. And now we can plug in both x of 5 and z of 2 into one of my original equations. So one of equation 1, 2, or 3, it doesn't matter. I'm going to use equation 1, because that looks fairly simple. X minus y plus z equals 0. So 5 minus y plus 2 equals 0. If I add y to both sides and then combine, I get a y of 7. So my solution is when x is 5, when y is 7, and when z is 2. And we always write our solution in alphabetical order. If there's ever a chance that it could happen like that. Does that make sense? So the whole concept is we pick two pairs and get two equations out of those two pairs with the same variable gone. And then I have kind of what I was dealing with before. And by the way, this is what you would do if you had 4 equations with 4 variables too. If you had 4 equations with 4 variables, you'd get it down to 3 equations with 3 variables. And you'd have to pick like 3 pairs and eliminate, whatever variable from each pair. And the same thing, if you had 5 equations, 5 variables, you just kind of you keep going down to 4 equations with 4, then you go down to 3 equations with 3, then you go down to 2 equations with 2, and then you, I guess, get 1 equation with 1, and then you solve that one, and then you kind of work your way back up. So that's the concept. Now, all of this is good algebraic technique, all right? But we're going to learn how to solve systems of equations using matrices in the back half of chapter 9. So in chapter 9, by the way, in 9.1, 9.2, there's some word problems. We are not going over those now, but we will get back to those, okay? So not this second, we're not gonna go over these. Basically, if you have word problems, you can use the matrix techniques too. So we're going to deal with matrices for a while. And essentially, I'm going to use matrices in 2 different ways to solve systems of linear equations. Right? Now, it's going to take a minute to set this up. So before we can actually solve the systems of linear equations, we're going to kind of backtrack and do an initial look at matrices. All right? So a matrix is just an array of numbers. So let me give you an example. Usually we put brackets around a matrix. Let's say I have 2, 4, -5, 1, 1, 8. So here's my example. This is what's called a 2 by 3 matrix. Or sometimes people would say 2 by 3 as 2 the x times 3. And what that means is it has 2 rows and 3 columns. Right, so 2 rows, 3 columns. This 2 by 3, that's called the dimension of the matrix. All right? So the dimensions of the matrix are 2 by 3. And the dimension of the matrix is important for the operations. Okay. So we're going to do 3 different operations on matrices. We're going to add, we're going to do scalar multiplication, and when you do add addition, scalar multiplication, that's going to be that's going to include subtraction. So some scalar multiplications like adding a negative, subtracting is like adding a negative. Does that make sense? So we're going to do addition. We're going to do subtraction, we're going to do scalar multiplication, and then we're going to do matrix multiplication, all right? And on each of those operations, the dimensions are important. Okay. So let's talk about adding or subtracting matrices. So if we have 2 matrices, and we want to add them together, if those 2 matrices are the same dimensions, the addition is simply component wise. Meaning, I'm going to take the entry that's in the first row and first column, and I'm going to add it to this entry, which is in the first row and first column. That'll give me a 2. Then I add these together. That's first row, second column. Then I add these together. That's second row, first column. Then I add these together. That's second row, second column. And I get that. Okay. So if dimensions match up, I'd simply add the 2 matrices together where each entry, each of the corresponding entries get added together. Okay. Now, if the dimensions don't match up, if I take 2, 4, -5, and 1, 1, 8, and I say, let's add that to matrix 3, 8, -5, 4. this doesn't exist. I can't add those two because they have dimensions that are different. One's 2 by 3, the other is a 2 by 2. So if the dimensions match up, my addition is just entry-wise. If the dimensions don't match up, then I just can't add. There's no, the sum there doesn't exist. All right. Any questions about that? It's pretty straightforward. So only add if the dimensions match up. Now, if we're going to be subtracting, and this kind of also leads us into scalar multiplication, let's say I have 2, 0, 4, 7, -5, 8, and I want to subtract 1, 3, 3, 2, let's do 6, -4. Well, just like when we were adding, we have to make sure the dimensions match up. If the dimensions don't match up, we can't subtract either. But you can kind of guess what's going to happen, right? We're going to basically distribute this negative into every single entry. And we're going to subtract in that way. So we do 2 minus 1. That gives me 1. 0 minus 3. That gives me a -3. 4 minus 3 gives me a 1. 7 minus 2 gives me a 5. -5 minus 6 gives me a -11. And 8 minus -4 gives me a +12. Be careful when you're subtracting a negative there. In fact, we're adding 4 on that last entry. So when you're adding or subtracting, dimensions have to match up perfectly. And if they do match up perfectly, it's just entry-wise. Now let's take a look at scalar multiplication. Remember, scalar is just a fancy word for a real number. So what's going to happen if I take a number like 6 and I multiply my matrix 2, 4, -5, 1, 1, 8. What would you guess is going to happen?
It'll distribute.
Yeah, just distribute into every single entry of the matrix. So 6 is going to distribute, multiply by 2, That gives me 12. 6 times 4 is 24. 6 times -5 is -30. 6 times 1 is 6. 6 times 1 is 6. 6 times 8. There we go. So scalar multiplication is fairly intuitive as well. All right. I hope, hopefully, scalar multiplication is fairly intuitive. By the way, hopefully you notice that when you're adding a matrix plus another matrix, I'll erase this in just a second. Since adding real numbers is commutative and associative, adding matrices is also going to be commutative. Doesn't matter which order you add them in, right? Scalar multiplication is the same way in that if I take a matrix and I multiply it by 6, or if I take 6 times the matrix, it means the same thing, right? So there's a commutativity about scalar multiplication and about addition that we have. Okay. I point that out because the next operation that we're going to do is not going to be commutative. It's going to be really different. Now, before I get to that next operation, I need to talk about some notation that you're going to see. Let's say we have a general 2x3 matrix. And we'll call it capital A because most of the time when matrices get a variable, we make it a capital letter. And a lot of times when real numbers get a variable, we make them lowercase. So a lot of our X's and Y's you've always dealt with are lowercase. One reason for that is because lowercase letters often signify a single number, whereas uppercase letters often signify a matrix. Not always the case, but that's a lot of the standard notation. So let's say we have a 2x3 matrix. Well, we're going to label that with entries A11, A12, A13. And then the next row is going to be A21, A22, and A23. So you'll see this notation in Moodle sum when it says, hey, add these two matrices, tell me what the entries are. What is the 1-1 entry? And what we're saying there is, what's the entry in the first row and first column? What's the entry in the first row and second column? So Aij is the ith row and jth column. So row I, column J. That's the standard notation for a matrix. I'm putting this out there because we're about ready to multiply two matrices together. And there's really some special stuff that we do when you multiply two matrices together. And I'm going to use that notation to describe how you multiply. Okay, does that make sense? All right. So here's the weird operation. Matrix addition is fairly intuitive. Scalar multiplication is fairly intuitive. Matrix multiplication is not intuitive. Okay. If I have two matrices, then when we multiply A times B, well, let me say it this way. I'll say if you have two matrices of the correct dimensions, then the product A times B is going to be another matrix let's say A times B equals C, where the entry in the I row and J column of our product is what we call the dot product of row I from matrix A and column J from matrix B. I know that looks like a long explanation, but that's a fairly compact explanation. Let me give you an example. Let's take two, 4, 1, 7, and multiply it times 3, -2, 0, 5. I'm gonna write and erase. This is the nice thing about having a whiteboard. It's not quite as nice about having notes with written with pencil in it. Is that I can sort of highlight portions of what I'm doing. So the first thing I'm gonna do is I'm gonna say this one is the one on the left-hand side. So if I multiply, if I want the 1 entry of whatever the product is, I want the 1 entry, I'm gonna take row 1 times column J, or column 1. So I'm gonna take this row 2, 4, and I'm gonna multiply times this column 3, 0. Now, the way I do that is via a dot product. So I take the 2 times the 3 plus 4 times 0. And whatever that number is, that number 6. That's the entry in the 1, 1 spot. That makes sense. Now, usually what I do is at this point, I say, okay, now I'm already focused on row 1. I did the first entry in row 1. Let's do the second entry in row 1. So let's do row 1, column 2. So I take the dot product. The dot product is when you take each one of these times there. That makes sense. So 2 times -2 plus 4 times 5. 2 times -2 plus 4 times 5 gives me 16. And by the way, I've run out of rows now, haven't I? So I've run out of rows. So that's going to end my matrix. Well, now let's go. I'm sorry, I misspoke. I ran out of columns, I should have said. I ran to the end of my row. I ran out of columns. I ran into the end of my row. Then I go back and I say, well, I've done all of row 1 times the respective columns. Now, let's take row 2. Times the columns. So row 2 in the first matrix times column 1 of the second matrix gives you the 2, 1 entry. That's 1, 3, 1 times 3 plus 7 times 0. By the way, that gives you 3. We okay with that? And then second row of the first matrix times second column of the second matrix gives you the 2, 2 entry. 1 times -2 plus 7 times 5. I get, I believe, 33 there. So the product of those two matrices is 6, 16, 3, 33. Now, here's an interesting thing that happens with matrix multiplication. If I multiply these same two matrices, but in the reverse order, now I'm using the rows from this one and the columns from this one. So what you would do is you would take row 1 times, I'm not going to keep drawing the circles every time, but times column 1. That'll give you the 1, 1 entry. Go get 3 times 2 minus 2 times 1 as the 1, 1 entry. Then row 1 times column 2 gives you 3 times 4 minus 2 times 7. You see where I'm getting those things? Making sense? All right. Then I go 0, 5, that row, second row. Second row, 0, 5. So 0 times 2 plus 5 times 1. Second row here, 0 times 4 plus 5 times 7. And if you calculate all those entries, uh, 6 minus 2 gives me a 4. 12 minus 14, I believe, gives me a negative 2. 0 plus 5 gives me a 5. 0 plus 35 gives me a 35. Notice that these two matrices are very different from each other. Okay? So what does that tell us? That tells us that matrix multiplication is not commutative. If I take two matrices, A times B, that is not always the same thing as B times A. There are special times in which they are, but those are special times, not in general. So matrix multiplication is not commutative. Now, I know I use these examples where we had 2 by 2 matrices in both cases. However, notice that really when we needed to multiply, really need is the number of entries in here in the row to match the number of entries in the column over here. The number of entries in the row is just the number of columns. The number of entries in each column is the number of rows over here. So let me explain what I mean by that. Let's do another example. Not of matrix multiplication, not commutative, that's just a no. But let's do another example. Let's take 3, -4, 5, 1. And multiply that times the matrix 1, 7, -8, 2, 0, -3. You might say, well, those don't have the same dimensions. I'd say that's all right. They don't have to have the same dimensions to be able to multiply. What I do need is I need the number of entries in a row to match the number of entries in the column. So now notice that, and again, this is sort of a visualization thing. I see this as taking this row and kind of flipping it up and multiplying it times these two numbers. I don't know if you, so I take this and I multiply like that. And then I take the same thing and I multiply like that. I take the same thing and I multiply like that. Okay. So I think of it that way. I'll write them down 3 times 1 minus 4 times 2. That's my first multiplication. By the way, that would give me -5, I believe. 3 times 3, -4 times 7, 0. 3 times 7 minus 4 times 0. Again, that's what I kind of visualize doing. Grabbing this row, turning it vertical, putting it on top of the column. And then 3 -4 times -8. -3. My last one. So I get -5, and then I get a 21, and then I get, what's that, -24 plus 12 is -16, is that right? I'll check that in a minute. And then I do the same thing with the 5, 1. 5, 1, I think of it as grabbing it and then turning it vertical and multiplying. So 5 times 1, 1 times 2. Five, 1, grab it, turn it vertical, multiply it by 7, 0. 5 times 7 plus 1 times 0. And I take the 5, 1, turn it vertical, multiply it by -8, -3. 5 times -8 plus 1 times -3. And if you calculate all of those, the first entry in the second row is 7. The second entry in the second row is 35. And the third entry in that second row is -43. So that's the final matrix. By the way, what if we reverse the order there? What if we took 1, 7, -8, 2, 0, -3, and tried to multiply that times 3, put a dot there, 3, -4, 5, 1. It doesn't work, does it? Because when I grab my row and then I turn it vertical, it doesn't match up. The dimensions don't match up well. And so this cannot happen. Or what I'll probably have you do is just write, this does not exist, D and E. Because the dimensions don't align nicely. Now I'm gonna use this as an example. Oh, that last example also showed that we don't have commutativity, right? Here, when you multiply A times B, you get a matrix. But here, when you multiply B times A, you can't even do that. So obviously commutativity doesn't work. Again, that shows commutativity doesn't work in general. But let me take a moment to talk about the dimensions of these matrices here. This first matrix was 2 by 2. This second matrix was 2 by 3. And we got out a matrix that was 2 by 3. It turns out, everybody see that? I'm just saying this example. I will write the general rule here, so you don't have to write that necessarily. It turns out that the reason why we could multiply is because the number of columns here, the number of entries in a row, number of columns, matched up with the number of rows here. So those match up. And when you think about this matching up, my final matrix is going to be dimensions 2 by 3. That makes sense? It's almost like dimension-wise, these got deleted. These deleted each other. Right? So, in order to multiply, A times B, A dimension N by M, then B has dimension M by B. And A times B will have dimension N by P. And so the dimensions have to match up that way. Okay. The number of columns in A has to match the number of rows in B for us to be able to do multiplication. Does that work? Now, I'm not gonna go through like showing this, but it turns out that while we don't have commutativity for matrix multiplication, we do have a lot of our other rules. Things like associativity. So matrix multiplication is associative. And just like when we do our distributive rule with real numbers, you can actually do a distributive rule with matrices as well. So while matrix multiplication is not commutative, we do have associativity, we do have the distributive property, we do have some other stuff. So matrix multiplication rules. All right, so AB is not BA, so not commutative. That's the big one. But if I have three matrices that I multiply, as long as I keep the order straight, matrix multiplication is associative. As long as I have the right dimensions, I won't go into that. So matrix multiplication, I'm saying for dimensions, we do have associativity. We also have a distributive property. You have to be very careful on the distributive property because if I take A times B plus C, when I distribute, I need to make sure that the A stays on the left-hand side since it was on the left-hand side over here. Okay, so we have the distributive property from the left. We also have it from the right too. If you go B plus C times A, you can do BA plus CA, but you have to make sure that the A stays on the right, okay, on both multiplications. So we have distributive properties. With matrix multiplication as well. All right. So it's not commutative, but it is associative. It does have the nice distributive properties that we want. as well. Does that all make sense? So these are the properties of matrix the basic algebra of matrices, right? This is the basic algebra of how do we add, subtract, multiply matrices, multiply by a scalar, et cetera, et cetera. Now, before we move on, I've been doing these all by hand, okay? It turns out that if you want to do these with your calculator is going to do the right things as well. So let me give you two matrices and, just mess with those. So let's take 3, 2, -1, 7, and we'll add 5, 4, 8, 0. And then we'll multiply those as well. And the dimensions are nice, so we can multiply those in either direction. That's kind of one of the nice things about square matrices, is that you can multiply when you multiply a square matrix times another square matrix. You guys know what I mean by square? 2 by 2 or 3 by 3, 4 by 4, those are all square matrices. So if you multiply square matrices of the same dimension together, you get back the same dimension. All right? So let's take a look at how we would treat that in our calculator. 3, 2, -1, 7 is our first matrix. I'm going to call that matrix A, so I'm going to refer to that as matrix A. And the way you do that, or the easiest way to do that, is to go into the matrix menu. See that there? Of your calculator. Now you're going to see 3 things at the top: names, math, and edit. When you're going to recall the matrix, you go to names, but we need to start by editing our matrix. So we're going to edit matrix A. So I just go to my edit, and then I hit enter or I hit 1. That'll bring up matrix A. So my matrix was a 2 by 2 matrix. So that's what it's asking you for up here at the top. It's asking for the dimensions. So we go 2 by 2. Now I have a 2 by 2 matrix. 3, 2, -1, 7. Was what I had as the entries for A. So I just have to put in 3, then 2, then -1, then 7. That work? So now, here's the thing, I have to quit and then go back into the matrix menu. And now I'm going to edit matrix B. That one was 5, 4, 8, 0. So it was a 2 by 2 matrix, 5, 4, and then 8, and then 0. So I got that right. Yep. And then I can go back to the home menu by second quit again. Now, if we want to add these, that's where I go into the matrix menu and I say, I want matrix A plus, then I gotta go back into the matrix menu, matrix B. So if I added those two matrices, I should get 8, 6, 7, 7. It should make sense, right? If I'm going to multiply A times B, I simply recall the name A, I hit the multiply, and then times B. Hit enter, and notice that that quickly calculates that for you. Right? So if you're comfortable dealing with your calculator, whoops, hit the wrong one. You can do a lot of operations really, really quickly. And if you wanted to take, a scalar multiplier, you can simply take 9 times your matrix, whichever matrix you want. Let's take 9 times the matrix A, and that'll give me a scalar multiple of A. And so all this stuff we just saw by hand, we can also do via calculator. Now, the reason I would bring this up is because in the next couple of sections, in 9.6, 9.7, we're going to solve systems of linear equations with some matrix operations. All right? The two operations that we're going to use, we haven't seen explicitly yet. But those operations, I'm typically not going to do by hand. I'm typically going to rely on my calculator to give me those. All right. So that's kind of what 9.6 and 9.7 are. They're going to say, well, we can use matrices to solve systems of linear equations. And I'm going to say, yep, we can. And not only can we do that, but we can do it very quickly if we rely on a calculator to do it, to do the grunt work for us. Okay. Does that make sense? Oh, by the way, let me just mention something. All right, matrix C is a 3x2 matrix that I already have in there. If I just recall, if I just hit C, you can see I get that one, right? If I try to take matrix A times matrix C, we know that the dimensions aren't going to work, right? Because one of them's 2x2 and the other is 3x2. So dimensions don't work. And if I try to do that, you'll see what my calculator does. It says, hey, this doesn't work. The dimensions don't match. There's a dimensional mismatch on the size of those matrices. The same thing if I were to add. If I were to try to add the two matrices, since these don't match dimensions exactly, you try to add them, you'll also get a dimensional mismatch. So your calculator knows how to deal with that, is what I'm trying to get at. It's programmed to give you back that this is not the right dimensions to use. Any questions? Being able to do that with our calculator just makes our life much, much easier. Okay. And so you can do those things with your calculator if you want, you can do all the operations, or you can do it by hand like we showed. And in the next class period, we're going to start out by solving linear equations with matrices using two different methods. All right, one of them is called the Gauss-Jordan elimination method. The other is using matrix inverses. And the shortest version of what I was going to say is you're going to go back to 9.1 and 9.2 and say, I should have done all of these problems with matrices because it's so much faster and so much easier using the Gauss-Jordan elimination or the inverse matrix operations. Does that make sense? So all of those things we did in 9.1 and 9.2 are going to be made much, much easier by the methods in 9.6. I should say easier, just quicker. All right? All right. So instead of starting 9.6 today and 9.7, those will go by pretty quickly. Next week, at the beginning of next week. All right, yeah, that's fine. I'll leave it here and we'll stop a few minutes early. Like that. And there you go. One thing I did want to say, oops, I forgot to do this. I mentioned this earlier, notation, very easy to figure out. But if you're dealing with, in the book, if you go in your homework in 9.5, here we're adding two matrices and we're getting a third matrix. If it's possible, I always just write A11, A12, that just means those entries, right? And then you just type in the entries, the corresponding entries. If it's not possible, you just write NS in every single blank, right? So if this was not possible, I'd write lowercase n, lowercase s in every single blank. Does that make sense? This one is possible, but so NS for no solution or not possible, no solution. All right, I will see you all next week. All right, see you then.